Hey guys, welcome back to another lecture video for Chem 104. In this lecture video, we will learn how to characterize the carbonyl family, and we'll also discuss the physical properties of two of its members, which is an aldehyde and a ketone. To begin, the carbonyl family is a very large class that's comprised of many functional groups. And so every single one of its members has one feature that's in common, allowing it to be part of the carbonyl family, and that is the carbonyl group. So the carbonyl group is simply a carbon that's double bonded to an oxygen. And so I'm going to add these terms, carbonyl carbon and carbonyl oxygen, to act as a point of reference. And so this carbonyl carbon is pointing to the central carbon, is referring to the central carbon that makes up the carbonyl group. And the carbonyl oxygen is the oxygen that is part of that carbonyl group. And so we can go ahead and just further characterize a carbonyl group based on its geometry. If you guys recall from earlier lectures, we can determine the electron geometry and the molecular geometry simply by looking at the number of groups of electrons that's surrounding the central carbon or the carbonyl carbon. And so here I have 1, 2, 3 groups of electrons. And since I have 3 groups of electrons, my electron geometry is going to be trigonal planar. Now for my molecular geometry, what I'm looking for is whether or not those groups of electrons are part of a bond or if they're lone pairs. And so once again, if I'm looking at this set of bonds, all of those electrons are participating in a bond, same as this and same as this. So here we have 3 groups of electrons that are all participating in some type of bond. And so therefore the molecular geometry is also going to be trigonal planar. So long story short, there's no lone pairs on that carbonyl carbon or the central carbon, making the molecular geometry and the electron geometry the same. And so what this does is it allows us to determine the bond angle, the relative bond angle, with respect to the carbonyl carbon. And so the bond angle for anything that's trigonal planar is going to be 120 degrees. And so if you have a full circle is 360 degrees, so this must be 120, and this also must be 120. Overall, what I'm trying to communicate is that when you have, since the bond angle is 120 degrees, if you're trying to represent a carbonyl group as a skeletal structure, you want to make sure that you bend your lines. And so if you, for example, have this very simple structure, since this vertice represents 1 carbon, and let's just say that's the carbonyl carbon for now, the bond angle that's representative of the skeletal structure is going to represent 120 degrees. Now when you guys are drawing this, you don't have to draw an exact 120 degree angle. All you have to do is just create zigzags, and it's going to be representative of 120 or 109.5. The list kind of continues. The main point that I'm trying to make is that the bond angle is not 180. If it's 180, then that means that we need to draw it as a flat line, which is something that we saw for alkynes. Okay. All right, so now that we have a better idea of these carbonyl groups and their geometries, let's go ahead and talk about the bond. What type of bond? I'm sorry, not so much the type of bond. Let's talk about the polarity of the bond. And so let me just go ahead and redraw this over here. And so here we have a carbonyl group, and what we're trying to determine is the polarity of the bond. The reason why we want to talk about the polarity of the bond is because it's going to dictate some intermolecular forces that we'll later discuss, which kind of rolls into this idea of melting point and boiling point, which represents the physical properties of specific functional groups. And so to determine the polarity of the bond, what we want to do is we want to take the change in electronegativity. And if you guys look at your chart, your Pauling scale, I think I gave that out a while ago. But nonetheless, if you guys take the electronegativity difference, that electronegativity difference is going to be above or greater than 0.4. So this is telling us that a carbon to a double bond to an oxygen, this bond is going to be polar covalent. And so since we have a polar covalent bond, that's going to imply that we have a permanent dipole pointing towards the most electronegative atom, which is going to be oxygen in this case. And so therefore, oxygen is going to have this partial negative charge, and this carbon is going to have this partial positive charge. And so there is a net dipole pointing towards the most electronegative atom, which is oxygen. All right, so now that we've kind of gone over some of the main features and main characteristics of a carbonyl group, let's go ahead and check out some of its members. And so these carboxylic acids, esters, and amides, these are very, very specific functional groups. However, one of the things that they have in common is that carbonyl group. So I'm going to go ahead and highlight it in yellow. And so here's a carbonyl group, here's a carbonyl group, here's a carbonyl group. And so this is just 3 examples. It's a very, very short list of the carbonyl family. However, I just wanted to draw in or give you guys examples, provide examples that demonstrates what these members look like. Okay. And so if you guys are looking at, for instance, a carboxylic acid to an ester to an amide, they're different in the sense of what else is bonded to the carbonyl carbon. And so their difference from one functional group to another is what else the carbonyl carbon is bonded to. So for carboxylic acids, we have this OH. For esters, we have this OR. For amides, we have this NH2. And the R is going to represent the R group, which is, once again, any alkyl chain or carbon chain. Okay. And so the main focus for the lecture today is going to be aldehydes and ketones. And so aldehydes, once again, they're part of the carbonyl family. So since they're part of the carbonyl family, they're going to have a carbonyl group. And so one of the covalent bonds that's on the carbonyl carbon is going to be an R group. However, what highlights a difference between an aldehyde versus, for example, a carboxylic acid, or an ester, or an amide, is the last component that the carbonyl carbon is going to be bonded to. In this case, it's going to be a hydrogen. And so if you guys have a carbonyl carbon that's covalently bonded to a hydrogen, then this whole section right here is going to be your aldehyde. And so there must be one, at least one, hydrogen on the carbonyl carbon. And so let's go ahead and talk about the identity of this R group. For aldehydes, the identity of this R group, it can range. It can be a hydrogen. It can be an alkyl chain or a carbon chain. It can even be an aromatic ring, such as like a benzene. Or just a cyclic ring in general. And so overall, this R group can take on a lot of different faces, if you will, which allows this aldehyde functional group to be prevalent in many different types of organic compounds, just because that R group can represent any type of organic compounds, really, in addition to hydrogen. Now, if you guys are trying to represent an aldehyde in terms of a skeletal structure, you must write, so when you guys are looking at a skeletal structure, remember that the carbons are represented as a vertice. And so this is one way that you guys can represent the aldehyde. So if you don't want to put in the lone pairs on the oxygen, that's absolutely fine. Just know that they're there, they're present, they're invisible. And so because we're talking about a functional group, when you guys are drawing the skeletal structure of an aldehyde, this hydrogen must be shown. And this vertice is going to represent the carbonyl carbon. And so this R group is going to be represented by any alkyl chain. So this is just one example of how you guys would incorporate this aldehyde functional group in your skeletal structure. So you must show the connection between the carbonyl carbon and that of the hydrogen. Okay. And so typically, once again, we ignore all the hydrogens that's on a carbon chain, but we don't do that for aldehydes because it's a functional group. So this portion right here is your aldehyde. And so I want you guys to notice that in this example, the aldehyde is found at the very end of the molecule. So typically, aldehydes are terminal functional groups. Basically, they're found in only two places. in this example specifically, they're found on the ends, they can be found on the ends of a molecule. So I can have another aldehyde here if I wanted to. And so because remember aldehydes are trigonal planar, I have to make sure that I represent that 120 degrees by bending my line. And so you guys will not be able to find aldehydes within a molecule. It's typically found at the very ends. All right, so let's go ahead and talk about ketones. So what do ketones look like? And so because ketones are part of the carbonyl family, we know that it's going to have a carbonyl group in which one part of its carbonyl carbon is going to be covalently bonded to this oxygen, and the other part is going to be covalently bonded to an R group. And so the point of difference between an aldehyde and a ketone is the identity of the substance that's going to be covalently bonded to the carbonyl carbon. For ketones, it's going to be another R group. Okay. And so remember, this R group is going to represent like any alkyl chains, and the list kind of continues. Okay. And so let me just write that down. So the possible R groups are going to be alkyl groups, cyclic compounds. You guys can add an aromatic. The only thing that this R group cannot be is a hydrogen. And so if this R group is a hydrogen, it's no longer going to be a ketone, it's now going to be an aldehyde. Okay. And so both of these R groups actually can be anything but a hydrogen. All right, and so once again, these R groups are any alkyl groups, cyclic aromatic rings, etc. Cannot be hydrogen. And so how would you represent them in a skeletal structure? And so if you guys are looking at the chemical formula or this generic representation of a ketone, these R groups are going to start with like a carbon. And so since either end of these carbons, either end of this carbonyl carbon are more carbons, then that means that ketones are typically found in the middle of an organic compound. So they are not terminal. They're anything but terminal. So I can have a ketone here, I can have a ketone here, I can have a ketone here, I can have a ketone here. And so these are, so I'm just going to put a parentheses here, and I'm going to extend this out. So typically, ketones are found in the middle of a carbon chain. Okay. So they are not terminal. If you have a carbonyl group that's found on the terminal ends of a carbon chain, then what you guys have is an aldehyde. Okay. One thing that I did forget to mention is this idea of R and R prime. And so your ketones, the identity of the R group can be different, or it can be the same. Okay. And so very similar to what we discussed for ethers, R and R prime. And so if you have RR, that means that they're the same alkyl group. If you guys have R and R prime, that means your alkyl groups are different. And so it looks like ketones has some freedom and some restrictions in terms of their R groups. The one thing that you guys need to remember is that ketones cannot have a hydrogen on the carbonyl carbon. Okay. And so what I want to discuss next is the physical property, or specifically the solubility of ketones and aldehydes. And so whenever you guys are talking about solubility of things, you're trying to describe how this ketone, this aldehyde, acts as a solute in solution. So in this case, we're going to think of these ketones and aldehydes as our solute. And when you're talking about solubility, you're going to put your solute in with your solvent to create your solution. And so what we're going to explore is whether or not when you guys place them together, they're going to form a heterogeneous solution, or if they're going to form a homogeneous solution. And so let's go ahead and explore the interactions that can be made between a ketone and an aldehyde. And so let's just say that we have this molecule here. Let me just draw it a little bit larger. And so I'm also going to draw in some water molecules. And so right now I'm just drawing the water molecules a little bit weird, just to kind of demonstrate a point. But obviously water, it looks like this. But I'm just showing, I'm kind of expanding it out just to prove a point. All right, so let's just say that these are the water molecules. You have this aldehyde, you place it in water. And so all of these water molecules are going to surround the organic compound. And for this organic compound to be soluble in water, in a solvent filled with water, it must be able to interact with these water molecules through intermolecular forces. And so remember that the carbonyl group is a polar covalent bond. And because it's a polar covalent bond, then that means that this oxygen is going to be partial negative, and this carbonyl carbon is going to be partially positive. And so what that tells you is that these partial positives and partial negatives can interact with water, since water itself is also polar. In other words, this oxygen is going to be partial negative, this hydrogen is going to be partially positive, this hydrogen is also going to be partial positive, partial negative, partial negative, partial positive. And so I'm just going to look at like one simple case here. So here we have this hydrogen that's partially positive. And so it's going to be attracted to things that's opposite of its charge, in this case, a partial negative charge. And so this type of interaction is known as a hydrogen bond. And it's not so much the formation of a hydrogen bond that allows this molecule to be soluble in water. The main point that I'm trying to get at is because we have a polar covalent bond in your carbonyl group, that carbonyl oxygen can interact with the hydrogen of the water molecule, which will be our solvent. And so for low molecular weight, or if you guys have an aldehyde that has small number of carbon atoms, then those types of molecules are more likely to be miscible in water. In other words, it's going to form a homogeneous solution. And so, however, if we start expanding our carbon chain, and so if we start increasing the number of carbons in our chain, the effect of this polar covalent bond is going to be diminished, and the nonpolar effect of these carbon and hydrogen bonds is going to be much more dominant for this type of molecule, such that when you have a long chain aldehyde or a long chain ketone, it becomes more insoluble or immiscible in a solvent of water. And so I know that I drew it for aldehyde, but the same can be said for a ketone. So let's just say that we have this ketone here. And remember, ketones, it's just two R groups. So let's just say that we have a small ketone. The partial negative charge on the oxygen is going to interact with a partial positive charge of the hydrogen that belongs to the water molecule. And so since those molecules can interact, they can kind of like, mesh with each other, and therefore this low molecular weight, low carbon number ketone is going to be miscible in water. And so I did mention that this carbonyl carbon is partially positive. And so, for example, if we had a water molecule such that it's oriented, such that the oxygen of the water molecule is oriented towards the carbonyl carbon, then there's going to be an interaction that can occur between the oxygen of the water molecule and that of the carbonyl carbon. And so once again, that also allows, that further allows the carbonyl group of that functional group to be soluble in water. And so the general trend for solubility for aldehydes and ketones, if you have 1 to 4 carbons in your aldehyde or ketone, then it's most likely that it's going to be soluble. When you guys get around to the 5 and 6 range, then it's going to be slightly soluble, going to insoluble. Okay, so you're going to start seeing some of it dissolve, but you might see a small layer of water. I'm sorry, small layer of your aldehyde or ketone that's going to be above the water. Now, if you guys have anything that's greater than 6, your organic compound that contains the aldehyde and ketone is going to be insoluble. Okay. And so that's going to be our trend for solubility of aldehydes and ketones. And once again, it's this idea of the polar covalent bond in the carbonyl group that allows this functional group to be dissolved in a solvent filled with water. So let's go ahead and talk about the physical properties, specifically melting point and boiling point for aldehydes and ketones. And so I'm going to abbreviate boiling point as simply BP, and melting point is going to be MP. And so what we're going to do is we're going to compare it to two things. First, we're going to go ahead and compare aldehydes and ketones to alkanes. And then we're going to go ahead and compare aldehydes and ketones to alcohols and see where they kind of line up or mash up. And so if you guys recall, if you have just an alkane, it's only going to be filled with carbons and hydrogens. And so if I have a bottle of the same alkane, I'm going to go ahead and move this around. The interactions that occurs when these two alkanes just kind of like bump each other in that liquid space, it's going to be a non-polar interaction. In other words, it's going to be London dispersion force. And so, once again, if you guys recall, London dispersion forces are very weak IMFs. And so if you have a very weak IMF, then that's going to mean that it takes very little energy for these two alkanes to be separated from each other. So low energy required for separation. So what we're going to do is we're going to magnify this concept, much like what we did in other lecture videos, with respect to melting point and boiling point. And so if only a small amount of energy is required for those two alkanes to be separated, then the melting point and the boiling point for alkanes is going to be small. It's going to be very small or very low. Now, when we look at aldehydes and ketones, so I'll just go ahead and draw a 2-carbon aldehyde for now. And so if I were to, duplicate this, and then also draw a 3-carbon ketone. And so I want you guys to recall that this carbonyl group is a polar covalent bond. So this can be partially negative, partially positive, partially negative, partially positive. And so if these two aldehydes interact with each other, their partial positives and partial negatives is going to allow them to do so. And the identity of this interaction is going to be a dipole-dipole. Now the same can be said with ketones. And so here, if you have a partial negative charge on this carbonyl oxygen, then this carbonyl carbon is going to have a partial positive charge. And the same pattern can be applied to the other ketone down at the bottom, where you have a partial negative and partial positive. And so once again, when these two interact, that interaction is known as a dipole-dipole. It's an interaction of a temporary, not temporary, but partial negative and partial positive charges. Okay. And so if you guys recall, dipole-dipole is going to be much stronger than London dispersion force. And so when that translates to concepts such as melting point and boiling point, when you guys are comparing that to, for example, alkanes, since alkanes have very small or low melting point and boiling point because their intermolecular force is very weak, a stronger intermolecular force, such as dipole-dipole, is going to require much more energy to be invested to physically separate these molecules apart. Okay? And so since it requires more energy, the temperature at which there will be an equilibrium between liquid phase and solid phase, or liquid phase and gas phase, melting point or boiling point, it's going to be much higher than alkanes. So the melting point and boiling point for ketones and aldehydes is going to be much greater than alkanes. And I believe on your guys' PowerPoint, I went ahead and showed some real data. And so you guys can go ahead and take a look at that in your own time. And so I'm just listing out the trend and the reason why the trend is like this. It goes all the way back to intermolecular forces and their relative strength with respect to each other. And so now that we understand that ketones and aldehydes, when you have a pure sample of them, their intermolecular force is dipole-dipole, let's go ahead and take a look at alcohols and compare the intermolecular forces found among alcohols to the intermolecular forces found among aldehydes or ketones. And so I'm going to go ahead and take a very generic alcohol. I'm just going to go ahead and do ethanol. All right, and so if you guys recall, your oxygen is it's highly electronegative. So therefore there's going to be a strong dipole pointing towards the most electronegative atom, which is oxygen in this case. And so I can represent that dipole as partial charges. such that the partial negative charge is going to be on the oxygen, the partial positive charge is going to be on the hydrogen. And so when these partial charges interact, the name of this interaction is going to be a hydrogen bond. And remember, there's two requirements for hydrogen bonds. One, there must be a hydrogen that's involved, and it must be really polarized. And the only elements that will allow that hydrogen to be polarized is fluorine, oxygen, and nitrogen, so Pon. And so notice that this hydrogen is covalently bonded to this oxygen, and oxygen is part of Pon. And we know that hydrogen bonds are stronger interactions than dipole-dipole. And so since alcohols exhibit hydrogen bonds and aldehydes and ketones exhibits dipole-dipole interaction, that's going to inform us that the melting point and boiling point for alcohols is going to be much greater than the melting point and boiling point of aldehydes and ketones. And so once again, if you guys were to look at your PowerPoint, I listed some values. So for example, I'll just go ahead and write one. Let's go ahead and do, so let's just say propanol is going to be 97 degrees Celsius, and I'm referring to boiling point for this example. And so since we're talking about propanol, this is a 3-carbon organic compound. And so what I want to do is I want to compare it to a 3-carbon version of a ketone or a 3-carbon version of an aldehyde. And so let's go ahead and just do propanal, which is an aldehyde. And its boiling point is going to be 49 degrees Celsius. Okay. And just to drive home the point for London dispersion forces, that's exhibited primarily, let me take that back. So every single one of these compounds can undergo London dispersion force, but the London dispersion force is primarily the dominant intermolecular force for alkanes. And so an equivalent version of an alkane is propane if we're using 3 carbons to compare all 3 functional groups. And so it turns out that propane has a boiling point of negative 42 degrees Celsius. That's far, far below the room temperature. And so this tells us that, propane, when we get it at room temperature, it's going to be already gaseous in state. So we've bypassed that boiling point of propane at room temperature. Anyways, as we go from propane to propanal, which is an aldehyde, to propanol, or 1-propanol, we can see an increase in boiling point temperature. And it parallels that of the trend in the strength in the trend of intermolecular forces.